that. Like our new picture shouldn't be like, oh, everything in quantum mechanics is mysterious, but rather, no, most of it makes sense from a classical worldview. And then there's this thin film of more nuanced stuff, which is where the real challenge lies.
How should we interpret quantum mechanics? That's what this conversation is about. I speak with Rob Spekkens, one of the world's leading experts in the field of quantum foundations, and also one of my own favorite lecturers. Here, we discuss inconsistencies in quantum theory, the role of observers, the relationship between wave function and reality, and much, much more. If you've ever wondered what conceptual challenges remain at the heart of quantum foundations, then this is the conversation for you. I'm Shane Farnsworth, and this is the Escape Sapiens podcast, supported by the Andrea von Braun Foundation. If you like what I'm doing here, you can have a direct impact on the success of this program by liking, subscribing, and sharing. And now, here's Rob Spekkens. I hope you enjoy.
Escape Sapiens.
So the first question, straight out of the gate, what is quantum foundations and what is the big problem it's trying to solve?
So the foundations of quantum theory, it's really about, in my view, understanding what this theory is saying about the world. Even though we've had quantum theory for 100 years of the modern quantum theory, 125 roughly years since sort of the first inklings of quantum theory, we still don't really have a consensus among physicists about what it really means. So the field of foundations of quantum theory is really trying to settle that to some extent. And so let me kind of do a bit of context building and tell you sort of why I think the study of quantum foundations is actually critical for the progress of modern physics. Let me talk about how important quantum theory is in science. So I think it's really interesting if you consider sort of the two pillars of modern physics, which is general relativity and quantum theory, and you look at them from the perspective of sort of what they explained and what technological innovations they led to. So for general relativity, the stuff that was in need of explanation, like the anomalies were, what's called the perihelion shift of Mercury, so an anomaly, that Newtonian mechanics couldn't explain. And then, after we had general relativity, it predicted deflection of light rays during eclipses, which were observed in 1915. And, since then, there's been, lots of astrophysical phenomena that you need general relativity to explain. So like most recently, black hole mergers, gravitational waves, all that sort of stuff. And in terms of applications, it certainly had some, like the global positioning system sort of requires general relativity to be precise. But then if you look at quantum theory and you say, okay, well, how was quantum theory born? Well, there was things like what's called the black body radiation spectrum, the photoelectric effect, things like specific heats. That's what sort of led Max Planck and Einstein to develop it. But the set of things that it explained is just almost everything, right? Like, it explained the periodic table of elements, the existence of isotopes, all of chemistry, reaction rates, molecular dynamics. I guess organic chemistry connects to microbiology, so it explains that. It explains, why stars shine, how nuclear fusion works, where the elements come from, the properties of matter, crystallography, all the like thermal, electrical, optical properties of everything. So basically, it explains all this stuff. And I would say it's sort of like all of science rests on quantum theory these days. And then when you look at the technological applications, well, there's the transistor. Modern world is built on computational technology, the laser, nuclear power, material science. So all kinds of materials we have, like long list. Maybe you could even include these days things like quantum cryptography, quantum computation. Those are coming down the road. But the bottom line is that if we had never discovered general relativity, I think the world would look very similar to what it does today. But if we had not discovered quantum theory, the world would be unrecognizable. Like everything in our world is sort of built on quantum theory, and most of science is sort of on a foundation of quantum theory. So it's incredibly foundational to sort of all the science we do. And so to me, it's a real travesty that we still don't properly understand it. The fact that we don't have a consensus about what it means we don't really understand it. So my view is that if we understood it properly, we wouldn't have this sort of controversy over how to make sense of it. And so there's still work to be done. And so I think, our ability to explain various phenomena will improve if we understand it better. And, the kinds of questions we ask, the kind of experiments we do will change. We'll be better able to achieve, pragmatic aims. Like if we want to build materials that have certain properties or, calculate chemical rates, all that will improve the better the technology, the better our understanding of quantum theory. So understanding the foundations, to my mind, is critical for making progress in physics, but also for the technological innovations that are going to come from that progress.
For someone who's never done a course in quantum mechanics, has no background, how can, in sort of a conceptual way, how is it possible that we can have a theory that's so successful, so experimentally it's one of our most successful theories, but at the same time we don't understand it conceptually?
Right.
They seem to be to contradict each other, these two.
Yeah. So it comes down to sort of a distinction in philosophy of science between sort of operational, phenomenological, empirical level. So descriptions of things in terms of sort of what's manifest to us, and then what people refer to as a realist understanding. So maybe something hidden below what's manifest, right? So there's that distinction, and so that distinction doesn't arise just in science. Also in our everyday life, most of us might be able to drive a car very well, but that doesn't mean we understand how the car works and how to fix it if it were to break down. And similarly, quantum theory is a kind of algorithm for if you have a experimental scenario that's been described in sufficient detail, you can use quantum theory to predict what the relative frequencies of different outcomes of measurements will be. But that doesn't necessarily mean what's really going on under the hood. And so another example of this from the history of physics would be thermodynamics was pretty well established. We had a lot of phenomenological laws about how the pressure, volume, and temperature of different gases are related to one another. We knew something about how temperature changes when you add heat, and we had a theory of thermodynamics that allowed us to predict a certain number of things, but we didn't have a deeper understanding, and that's what the field of statistical mechanics provided. So this is like around 1900s. The atomic hypothesis was still controversial. There were people who said, no, we don't need to posit atoms. We don't need to understand things on that deeper level. But progress in chemistry and in statistical mechanics showed that actually, having that deeper description provides explanations of phenomenological laws. Things we didn't understand were now explained in terms of that deeper level. But it also led to a lot of progress in terms of just expanding what you knew even at the kind of manifest level. Your understanding of thermodynamics improves once you have statistical mechanics. So the idea is that it's the same with quantum theory. We have a pretty good kind of phenomenological account of things in quantum theory. But some of us think that, there's more to understand at this deeper level. We need to understand quantum theory under the hood.
So then what are the key things that we don't understand? So if you're
Right.
going to lay down the postulates and say, here is a smoking gun for a problem.
Right. Well, maybe before I get to the sort of problems, let me say a little bit about maybe what the main activities in the field of quantum foundations are.
Sure.
Kind of it'll set the stage. So I think it's useful maybe to think about sort of three main activities. So one would be interpreting the formalism of quantum theory. So sort of coming up with the correct interpretation. And the second would be kind of understanding what's innovative about quantum theory relative to classical theories. So what has really changed in a quantum world, in terms of what principles hold relative to our older classical theories. And then third, essentially developing new frameworks within which we can sort of talk about different ways the world could have been. So not just contrasting quantum theory to classical theories, but all of the ways the world might have been. So there's been a lot of work, sort of frameworks for the landscape of possible physical theories, and then it helps you sort of figure out what principles might pinpoint quantum theory within that landscape. So okay, on the first one, interpretation. Some physicists think that this isn't really legitimate science to sort of ask about the interpretation of formalism. It's sort of got a bad rap, and it's sometimes considered just some sort of appendage that you want to add on to the theory that's not really doing anything. So I think that's mistaken. It's not of that type.
Can I stop you there?
Sure.
When you say an interpretation, what do you mean exactly? So Copenhagen, many worlds, these are interpretations, right? That's what you mean.
Right, yeah. So the biggest distinction, I guess, would be between, different philosophies of science. So one of the biggest divisions among interpretations would be, whether you're an empiricist or a realist. So roughly speaking, people have a more empiricist leaning in their philosophy of science. Will say, well, look, the role of a scientific theory is to just make predictions for well-described experimental procedures, and if your formalism does that, that's all it really needs to do.
Yeah.
And I think among people who are persuaded of that type of philosophy, there's kind of less disagreement about how we should make sense of quantum theory. But then there's the realists who say, no, that's not the purpose of scientific theory. It should also offer an explanation, and we should have some sort of deeper understanding. And different realists have different notions of what realism means. For me, the critical thing is that when you have, for instance, correlations, there should be some causal explanation. Did this cause that, or was there a common cause? If your phenomenological account doesn't answer that question, then it's wanting, in my view.
And so people attack the exploration of different interpretations.
Yeah, I think, in some cases, there's an attitude that these operational or empiricist approaches are just fine because that is the purpose of science, and looking for a deeper realist interpretation is somehow inappropriate. So, Copenhagen is, a name we give for a cluster of approaches which really do take that kind of approach. So, Heisenberg and Bohr were very empiricist in their approach, and they thought that they had a formalism that you didn't need to add anything to it. It described the story. But then on the other side, like the realist, you have a bunch of options. So Everett you mentioned, but you also have the de Broglie-Bohm pilot wave theory. You have collapse theories. You have various approaches that think that the theory of inference needs to change. So you have quantum logic, quantum Bayesianism. Hidden variable models. You have a long list of approaches that are trying to come up with a realist interpretation. And I would say, that's kind of the whole gamut of interpretations.
And so I initially kicked you off trying to find out what were the problems with quantum mechanics. So what's wrong with the postulates that we have?
Okay. So I'll interpret that question. I mean, if you go into the literature, there's lots of work on sort of what postulates should you derive quantum theory from. But in a way, it's useful to start with sort of the textbook presentations of quantum theory. So like if you look at a lot of textbooks, there'll be a list of postulates. And among them are things like the physical state of a system is described completely by a wave function, or more abstractly, a ray in a Hilbert space, but some mathematical object. And the first axiom is that that's all there is to say about a system. And then there's an axiom about what the dynamics of that thing looks like. So if you have a system that's isolated and it evolves, then there's some mathematical way of describing that evolution. But the key thing is that it's deterministic. It's continuous over time. And then you have this axiom which talks about what happens as the result of a measurement, right? That, okay, now your wave function changes in a way that is discontinuous and indeterministic. So that's the usual kind of source of the problems, those two axioms. So the first problematic thing you could say is that the textbook axioms are kind of a Frankenstein monster of sort of realist and operational concepts, right? So on the one hand, you're talking about systems and their physical states and how they evolve. And on the other hand, you're wheeling in this notion of measurement, which is this very anthropocentric thing. And so you can kind of go two routes here. You can say, let's try to make it purely phenomenological operational, or let's try to excise all the operational stuff, all the reference to measurements. So you can say something like, well, think of the wave function not as a description of the properties of a system, but rather maybe just the mathematical thing I use to represent some preparation procedure in my lab. So if I do things differently to set up my experiment.
More like a state of knowledge.
Well, I wouldn't say state of knowledge necessarily. I would more say, like, rather than being associated to some microscopic degrees of freedom and some notion of what properties they have, I say, no, there's something I've done in the lab to set things up before I hit go. And who knows what's going on, what comes out of that aperture. But like that whole setup, if you describe it for me, I should be able to associate a wave function with it, which helps me predict what outcomes are coming. And so, you can reframe the postulates just in terms of, it all relates back to experimental operations. And that works pretty well. And what you get is the sort of minimalist interpretation of the formalism, which tries to be non-committal about the systems and the properties or anything like that. But if you go the other route and say, okay, I want to eliminate the operational stuff, and I just want to describe systems and their properties, things like that, then you really want to not have any axiom that refers to measurement, because after all, a measurement is just a collection of atoms, and when I do a measurement on a system, I'm just interacting all those things together. So I shouldn't have to stipulate anything above and beyond the usual dynamics. So you can try to set out postulates like that, but that's where all the disagreements come in. That how do you excise the operational notions from the axioms? Well, some people would say, if you stick to the idea that the wave function is this complete representation of everything that's going on, then you get a contradiction between these two remaining axioms. If you imagine that a measurement is just a collection of atoms interacting with your system, and you sort of include all of that and say, how is that going to evolve? The postulate that tells you how isolated systems evolve says, the whole thing's going to evolve deterministically and continuously over time. And that seems like you cannot thereby sort of reproduce an axiom that would say things are going to evolve indeterministically and they're going to be discontinuous over time. So that's the tension that we usually call the measurement problem that people are trying to resolve in their realist interpretation. And how you resolve that kind of determines what interpretational camp you land in. So you could say, the postulate that says all evolution is deterministic and continuous is not correct. That's only true for small systems that are isolated, but large enough systems, actually the fundamental dynamics is indeterministic and discontinuous. And there's something called collapse theories or dynamical collapse theories, which sort of take that point of view, and their objective is to sort of have a new dynamics which sort of approximates this deterministic continuous dynamics for small systems and approximates well the sort of measurement dynamics for large systems.
So can I stop you there and ask? So the first postulate is that you have a Rayner-Hilbert space, or you have some wave function that describes all of reality. The second postulate describes how the wave function evolves in time.
Right.
And the third one is the collapse of the wave function, the measurement. And so in these collapse theories, are you saying that they try to, in some sense, derive the second postulate, the evolution, from the third? Or
no, they're just saying that the second and third postulates really are just two limiting cases of a single dynamics. And so for instance, some of these collapse models would say, every particle in the universe does get sort of localized, and so it undergoes a discontinuous indeterministic dynamic. So it will be localized in different places with different probabilities, but very infrequently. And therefore, if I have a single atom going through an experiment in my lab, the chances that I get localized during my experiment are very low. And so I can do this lots of times and never see this. But if I now take an apparatus that has 10 to the 23 particles in it, and it sort of starts going into a superposition of, like maybe my pointer goes into superposition being here or here, well, the chances that one of the particles in that pointer gets localized in a short time are actually very high. And so that's the kind of game they play, where they want to say, okay, in these two limits, highly composite systems or very simple systems, I'm going to get approximations to these two types of dynamics.
And so then do they have a more fundamental postulate sort of in both limits goes, reproduces?
Yeah, they sort of posit an alternative to the Schrodinger equation, which is the usual equation that governs the deterministic continuous evolution. They want to say, that's not the fundamental equation. The fundamental equation actually is different, and it has a kind of stochastic dynamics as well. So there's some randomness, things like localizations of particles. And so the set of particles in the universe obey this equation. And it's just that, on short time scales, if you ask what does that equation imply for, a single system going through my lab, the answer is going to be, it'll look indistinguishable from Schrodinger. And if you say, well, what does it imply about the dynamics of a pointer on my measurement device? It'll look just like the collapse postulate. So that's the kind of picture they have.
And are these models complete? Are they complete in the sense that they're internally consistent and they work in all experimental regimes, or?
Well, they certainly make different predictions from a standard quantum theory. So, some people are engaged in trying to put bounds on these models. So you could potentially rule them out experimentally. So if you were to set up a coherent superposition for some large object So there are some experiments today involving cantilevers, and these. I can't remember what the most massive object we have in superposition is, but at some point you would expect to see a deviation. That you would expect to see something different from what standard quantum theory predicts. And if standard quantum theory is vindicated by those experiments, it puts pressure on these collapse theories and says, well, this is probably not right. So yeah, you can disprove them experimentally with these kinds of experiments, but the experiments are challenging because if you have a large system, it tends to interact with its environment, and so it's very hard to kind of keep it isolated.
And so you're not sure what you prove at the end of the day.
Well, yeah, if that's right. If you're not sure whether you've really kept it isolated, then its interaction with the environment can kind of simulate this collapse mechanism. That's right. So you have to be careful about interpreting the results of those experiments.
So in sort of minimalistic quantum mechanics, sort of the minimal approach, what is an observer there? So if I have two particles that just collide or bounce off one another, is that an observation, or do you really need to have someone who's conscious come along and be turning the dials?
Yeah, so I guess there's a kind of a branch of interpretations where, so I would put this under the kind of postulate about the dynamics. So like I said a moment ago, some people believe in these dynamical collapse models, which say that, okay, the Schrodinger equation is not fundamental, there's this modification of it. And then there's a camp which says something like, well, actually, dynamics is not always Schrodinger equation, but what makes the difference is not, how big the system is, but rather, is there some conscious observer who's come and looked at it? That's a very fringe point of view, though. I don't know anyone today in foundations of quantum theory who really buys into that. So it's not a very popular point of view. I think in popular science treatments, you hear a lot about, reality is influenced by the observer. But yeah, most interpretations of quantum theory don't take the observer to have some sort of causal impact on the evolution of systems. Yeah, I would say that's not. I mean, most of these interpretational strategies treat an observer just like an apparatus. We're also a collection of atoms, and when we interact with the system, if everything evolves deterministically and continuously according to the Schrodinger equation, then we also become entangled. So that's a particular kind of quantum correlation, entangled with the measurement device and the system. And it's a way of thinking about the measurement problem that not only is it kind of inconsistent with the idea that there's some sort of indeterministic evolution, that this is what the collapse rule usually tells us, to imagine that we just have a unique evolution into this bizarre entangled state of observers and measurement device. But it also says that there's kind of like there's not a single thing that the observer has observed. Like you'd expect them to just sort of have one outcome. So yeah, one of the strategies of how to avoid the measurement problem is to deny that what we consider as sort of alternatives, like either this outcome occurred and say the up outcome occurred and the observer saw up, or the down outcome occurred and the observer saw down. One strategy is to say, both of them occurred. And that's the Everettian strategy, that these things that we think of as possible worlds are in fact all realized in parallel. And so the Schrodinger evolution describes this sort of multiverse of possibilities, and that thing evolves deterministically. But from the subjective point of view of individual observers living in the world, they have this illusion of indeterminism because they're sort of just stuck in their branch and they see only what's happening in their branch. So that's how they sort of break the resolution. There's like an objective determinism at the kind of multiverse scale, but there's this subjective indeterminism from the perspective of the observers in each branch.
Do you have a favorite interpretation, or do you have an interpretation that you really follow?
Well, we can talk a lot about that. I guess I would say, in terms of the measurement problem, the one alternative we haven't talked about, it would be denying that first postulate, the representational completeness of the quantum state.
Okay.
Right. So if you say, well, I don't believe that the quantum state represents everything there is to say about the physical system, then you're positing that there might be some additional variables, which are usually called hidden variables. And the way you could resolve this tension is to say something like, the particular outcome of the measurement that occurs depends not only on the wave function, but on the values of these hidden variables. And that is still consistent with the wave function evolving deterministically, because it's the hidden variables that determine what outcome gets observed. So
go on, sorry.
I was going to say that there's sort of two, in my view, there's two varieties of hidden variable model. one that I'm enthusiastic about and one less so. So one of them just says, well, the wave function still describes something real, but we need to supplement it with other degrees of freedom. And the other says, the wave function actually is more like a probability distribution over something else that's what's real. And so the jargon there is psi-ontic. So psi is the notation we usually use for the wave function. So if you're treating the wave function as real, those are called psi-ontic, the Greek ontos meaning real. And the case where the wave function is meant to represent, an incomplete description of our knowledge of the underlying reality, that's called psi-epistemic. The same root as epistemology, about knowledge. So I'm in the. I mean, there's much more to say, but I think the character of the quantum state, the wave function, is it's a state of knowledge, not a state of reality. But there's a lot more to say about what kind of interpretation can work. There's a lot of constraints on how that can work. But now we've sort of gone over the main sort of interpretational strategies, and sort of relative to the textbook axioms, I think it's that representational completeness axiom that's problematic, and that's sort of how you escape the measurement problem, in my view.
Is that sort of a unique position to hold? Because most people, I would say, look at the third postulate, the collapse postulate, as being the problematic one. And so you see the second and third as being probably fine, and the first is the one that you really point out as being problematic.
Well, I'm not sure what notion of most you have in mind. I mean, certain people who are enthusiastic about the many worlds interpretation would say, yeah, that one's just got to go. And the whole notion of kind of measurement collapse is just this subjective illusion that observers have. But in other interpretational camps, so in the de Broglie-Bohm pilot wave theory, you also have a kind of deterministic evolution of the wave function, but now you have these hidden variables that sort of pick out particular outcomes, and so you do still have that third postulate, like the measurement update rule is still valid and correct. And similarly in collapse theories, they think that one's more important than the others. But yeah, I think you're right. To some extent, if you are denying the representational completeness of the quantum state, the tension between measurement and the dynamics of isolated system, it just feels less pressing. It's kind of like it's not your main concern. It's kind of like I settled that. Now I have new problems. So it's kind of like it's a very different set of problems that you have in the interpretation project if you go this route. So in that sense, yes, maybe not so many people go the route of treating the quantum state as a state of knowledge, and now we have all these new problems, and the measurement problem is not one of them. So that is uncommon, yes.
So before talking more about states of knowledge and states of reality, just quickly, when I look at the work when I look at work in quantum foundations, what I often see is that gravity isn't taken into account, or the standard model isn't taken into account. Is it clear that we should be able to resolve the issues with quantum mechanics without also being able to, at the same time, resolve quantum gravity, or without bringing in the standard model? That we can really treat quantum mechanics in isolation on its own and solve these problems?
That's a good question. I mean, it's conceivable that progress that comes from thinking about, say, quantizing gravity could impact our thinking on the foundation of quantum mechanics and our thinking about what the correct way to interpret this theory is. That's certainly possible, but I guess personally I imagine it's going to be the other way around, that to some extent it seems to me that if we are confused about what this theory means, then maybe it's not so surprising that we haven't been able to understand
quantized gravity,
how quantum theory and general relativity fit together. So if we had a better understanding of quantum theory, then maybe it'll become more evident how we can solve this problem. And I think just to go back to sort of why is interpretations of quantum theory important at all? I mean, my view is that there's a bit of an illusion sometimes in popular science and among physicists that this quantum theory is this done deal. It's this monolithic thing that we can just look at and it's not changing or anything. That's not really the case. The quantum revolution is still ongoing. Quantum theory itself is changing, and it's not as if it's unambiguous how to apply it, right? So the view I take of quantum theory will inform how I approach the problem of unifying it with general relativity. So we were just talking about, is the quantum state a complete description, a description of reality, or is it a description of what I know about reality? That'll have a huge impact on sort of how I approach the question of how should I unify this with general relativity. But less prosaically, there's lots of other examples. Like if I look at chaotic dynamics, there's big disagreements about how should we define chaos in a quantum world as opposed to a classical world. Like so, maybe the obvious analog of sensitive dependence on initial conditions kind of doesn't go through, and so then it depends on how you think about the formalism, how you're going to do that. And then more generally, there's all these frameworks that people look at. So things like information theory, the theory of computation, something called algorithmic information theory, which is about the complexity of strings, or machine learning ideas, or figuring out what caused what from correlations. That's a field called causal inference. Lots of people want to ask, well, what's the impact on those frameworks, those sorts of theories in a quantum world? And all these frameworks come with a set of concepts and how to think about problems, and how you think about quantum mechanics impacts what you think the quantum analogs of all that is. So quantum information theory, different points of view in quantum theory will lead you to make progress in different ways, right? So to some extent, like how you think about quantum theory has a huge impact on the kind of progress you make, the kinds of questions you ask, your chances of making good progress.
Do you think, so this is a little bit out of left field, but we're currently in the process of building quantum computers. That's
Right.
what people are trying to do at IBM and Google and so on. Do you think now that we have engineering involved in, it's really quantum foundations,
Okay.
foundational questions, do you think now that we have engineers on the problem, it's going to help our understanding of the fundamentals of quantum mechanics? Or do you think we won't get feedback in that direction?
Maybe yes and no. That a lot of the kind of day-to-day activity of some of these quantum engineering problems, like let's say I want to build new quantum algorithms, like find problems for which quantum computers offer an advantage, or work on better architectures. I think a lot of those things won't impact the foundations of quantum theory. But I think the quantum information revolution, for example, was this huge boon to the foundations of quantum theory because it expanded the scope of things that needed explaining to some extent, right? That if you really understand quantum theory, you ought to be able to have a deep understanding of why it is that there's some advantages for the purposes of computation, right? And what sorts of tasks will you expect to see a quantum advantage for? So you could say that this is a good litmus test for different interpretational programs. Does it offer us any insights on sort of the quantum advantages that quantum technologies provides for us? And so, I think a lot of the innovations that have happened in the foundations of quantum theory, since the mid-90s have been very much informed by kind of looking at quantum theory in this new way from the lens of information theory. So certainly I was thinking a lot about quantum information theory, when I started in the field, and it definitely changed my view of what the theory was saying. It's a very different perspective on the formalism. And so it's had a lot of impact. And so, every time I think there's a new technological application where you can show, there's some advantage by virtue of being quantum, it can kind of feed back to the foundations by having a new target of something you need to explain, something you need to do justice to.
So then, if you are trying to argue that the wave function is a state of knowledge as opposed to a state of reality, what's the key evidence that we have for that? Okay,
so that's a very long story. I'll try to make it brief. I mean, to me, and I should say this is, now we're very much closer to like my own research program. So first I'll say one way to characterize what I've been thinking about for most of my career is a challenge that an American physicist by the name of E.T. Jaynes set down. So he had this really nice quote that says, quantum theory is a peculiar mixture of epistemological and ontological elements. So, the facts about what we know and facts about what exists, all scrambled up by Heisenberg and Bohr into an omelet that nobody has seen yet how to unscramble. But, that unscrambling is a prerequisite to, progress, because if we don't know if we're talking about what we know or what is, we just don't know what we're talking about. And so I really believe that. I feel like, okay, we need to come to the formalism and disentangle what in that formalism is about reality, totally independent of any observer, and what in that formalism is describing what some observer knows. And it's not as if that's a new distinction. Like if I look back at statistical mechanics, and we talked a little bit earlier about how thermodynamics is a lot of thermodynamic phenomena are explained by this theory where you have a large collection of atoms and you have limited knowledge of really what's going on. So, in a Newtonian universe, every atom has a position momentum. But when I just have a gas in a box, I know very little about that. I don't know the positions and momenta of all the particles. And so, one way to think about that is that you have this limited knowledge, right? You could say there's many, many possible states that are consistent with the very limited data I have. And now let me make inferences based on that. For every one of those states, here's how they would all evolve. And so, there's some predictions that are very reliable. Like I can say, I know that if I increase the temperature, then at fixed volume, the pressure will increase. Things like that I can infer in spite of having a huge ignorance about what's going on. So the kind of distinction between what elements of the formalism are about what we know and what elements of the formalism are about what really exists is already there. So like the position and velocity of all the particles, that's a part of what is really there. That's describing properties of the system. Whereas terms like the microcanonical ensemble, or you think of it as a probability distribution over all the possibilities for those position and velocities, that's a description of what we know, right? So like when I only know the volume and temperature, then here are all the possibilities for the microstates. So that distinction between what is and what we know is already there in physics. And the claim is that we need to understand in the quantum formalism, how to draw that line. What aspects of the formalism are about what is, what aspects are about what is known.
Yep. Why is it more difficult in this case than in the classical?
Yeah.
Why is it in some sense obvious to us in the classical case but not?
I think, in the classical case, yeah, it's a good question. Why is it more difficult? Maybe because for a lot of thermodynamics, for example, you could get away with the pictures of reality that came before, like so Maxwell's theory of electromagnetism and Newton's theory of sort of particle dynamics. You could take those ideas about how to describe reality, kind of add to it the fact that we're ignorant about a lot of it, and get predictions that match up quite nicely with a large part of thermodynamics. So things went smoothly for a while. We kind of already had a notion of what the reality ought to be. Whereas in quantum theory, we're kind of not given that division. We have to work that out for ourselves. And so it's very much more like a kind of cryptographic problem that you have this sort of omelet. You got a formalism, it works well, but you need to disentangle what's what. Yeah, I don't know if I can do it more justice than that. In a way, like the formalism works well, but it doesn't come with any kind of guide for how to think about different aspects of the formalism. Whether to categorize this as part of reality or part of what we know. In fact, even what the formalism is not fixed. Like if quantum practitioners, there's different formalisms you can use. So most students will learn the Hilbert space formalism, and there's different variants of that called the Schrodinger picture and the Heisenberg picture. But anyways, it's a particular formalism. And then there's this totally different thing called the path integral formalism, which does the same calculations but extremely differently. It looks totally unlike. So that people who do field theory use that a lot. And then over in the quantum optics community, they like to use these real valued functions over phase spaces to do exactly the same calculations. And so we have all these different formalisms. And again, it's not clear for any of them how to disentangle, what's about reality, what's about knowledge. So yeah, we're sort of in a sort of decipherment position that we have this stuff, and nobody's told us how to unscramble the omelet. We just kind of have to figure it out.
So one aspect that I find conceptually quite difficult to wade through when it comes to seeing the wave function as a state of knowledge is interference. So if I look at, say, diffraction, my conceptual view of diffraction is I have the wave function sort of interfering with itself, and that's what causes the pattern on the sort of the sheet at the end of my experiment. So if your view is that the wave function is a state of knowledge, how do you get these this sort of diffraction and sort of interference behavior? If the wave function isn't something that's physical, it's just it's our imagining of what is there in some sense.
Right. So first off, interference is something that can arise in a classical theory of waves where I have no ignorance at all, right? Like if I have classical waves. And so the puzzle of a quantum interference experiment is not just merely the existence of an interference pattern, but it's actually a tension between, on the one hand, the existence of an interference pattern if I don't bother to try to figure out where the particle went. And on the other hand, if I go and probe and try to figure out what path or what slit the particle went through, then the interference pattern goes away. That's sort of the puzzling thing, that merely acknowledging that you have a classical wave theory, it wouldn't explain the second fact. Like, if it was a classical wave theory and I have waves going through two slits, if I went and looked at the wave in this slit, it wouldn't change the fact that there's interference down the line. So the real kind of mystery, I guess, is how do you have this kind of duality of wave-like behavior and particle-like behavior? How do you explain that? And how is it that thinking of the quantum state as a state of knowledge helps, or how can you do justice to that? So together with some collaborators, we wrote a paper about this a few years ago. There's a very simplified version of the double slit experiment, which is a Mach-Zehnder interferometer. So you have basically a particle, like a photon maybe, and it goes through a beam splitter, and then it just has to, it either gets reflected or transmitted, so it goes just along one of two paths. And then you can use mirrors to recombine them at another 50-50 beam splitter. And what you find is that if you balance things nicely, then you will get all of your photons coming out just one of the output ports of that final beam splitter. And if you now introduce a phase shift, like using a piece of glass, you can introduce a phase shift on one of those two paths, you can actually make it so that the destructive interference happens at the top rather than at the bottom. So now you can have all the photons coming out the bottom rather than at the top. So that's your analog of interference, right? You have like a dark port and a bright port, and you can toggle which one is which by doing this phase. Meanwhile, if you go and you measure and ask, is the photon in this path, you end up destroying the interference. Now you get 50-50 probability of finding on either output port. So that's, the whole mystery of wave-particle duality can be expressed in terms of this Mach-Zehnder interferometer, which is just a small variation of the double slit experiment. And so what we show in this paper is that the key thing to some extent is to imagine that your wave function is a description of knowledge, but not about a particle and its degrees of freedom, but about the different modes of this interferometer, so the different paths of this interferometer, and their degrees of freedom. So, a particle is like this localized thing, and the kind of degrees of freedom it has are like a position or a momentum. Whereas, if I think of field theories, Maxwell's theory, for example, then the systems change. The systems now are things like, this mode here, this path. And the degrees of freedom are more sort of excitational degrees of freedom. So there could be, an amplitude of a field. It could have a phase, for instance. And so sort of the systems and their properties change quite dramatically as I go from a particle picture to a field picture. So what we were able to show is that, in the Mach-Zehnder, you can imagine a kind of classical explanation of what we just described in terms of, simple degrees of freedom for each mode. So I should say all of this was really just a generalization of some older work I did on something called the toy theory, which sort of is just trying to explain how two-level quantum systems work. So here the idea is that every mode has four possible physical states. And you can think of them as just two binary degrees of freedom. So one degree of freedom is this mode occupied or unoccupied? And the other is just, does it have phase 0 or phase pi? So it doesn't even have the possibility of all phases, just these two possibilities of phase and these two possibilities of being unoccupied or occupied. But the critical thing is that even the kind of unoccupied mode still has this phase degree of freedom. So unoccupied just means that, if you put a detector there, you won't see anything, but it still has some information carrying capacity, for example, like it's either phase 0 or phase pi. So when you have this simple model, you can show that, whether a photon goes left or right at a beam splitter depends on the relative phase of the two modes that are coming in. And so if I start out with only one mode occupied and the other unoccupied, I sort of preserve that along the way. And which of the final modes is occupied is sort of a function, just a deterministic function of this hidden state. This is a hidden variable theory. And so you can explain the interference phenomena by saying, well, when I put the phase shifter on one of the arms, it changes the local phase. Remember, it could be 0 or pi. And that local phase change influences the relative phase of the two modes. And that's what determines which way the excitation ends up going. So you can explain the interference part. And then the kind of part where if you look at it, you destroy the interference, the way that is handled in the model is that if you learn whether something's occupied or unoccupied, you randomize the phase. And so when I look here and I don't see the particle, then I still have an impact on it. I change its phase. And that's what makes it equally likely to come out either port at the end. OK, so I've tried to describe the details. But the bottom line is that one way of thinking about the mystery of all this would be to say something like, when I go and look here, sometimes I don't see the particle. I learn that it was on the other port. How did it know that it was not allowed to appear in the dark port anymore? It never went near this detector. How could it know that now it's not allowed to exhibit interference? That's the usual puzzle. Like even Feynman described it this way. Like if I look at this slit and find that it went through the other slit, how does it know whether it's allowed to make interference patterns? And the answer we provide is that only if you think that the fundamental kind of hidden ontology is particle-like, is that a mystery. If you think, OK, these modes, they have their internal degrees of freedom, then when I come and I don't see the particle here, I still have an impact on the physical degrees of freedom of that mode, which propagates in a totally causal way down the line. It has had its phase randomized, and that impacts what happens further on. So to some extent, in this model, the quantum vacuum is not nothingness. And the mistake of the puzzlement of these old stories was to think that, oh, if I don't find the particle here, then there's nothing here. And there's no possibility of transmitting any information about whether that detector was in place or not. Well, actually, no, there is. It still has a phase, even though it's an unoccupied mode. And that can transmit information forward. And so critical to that whole story is the fact that the quantum state is a probability distribution over these physical states I described for you. And that's why we get sort of these relative frequencies of different outcomes. So yeah, that in this approach where quantum states are states of knowledge, you can take that part of the phenomenology of quantum theory and say, actually, it's not in tension with classical physics at all. I can have an underlying hidden variable model of that's totally classical and that explains what we've seen.
But in this case, do you need non-locality to make it work? Is that what you're saying? No,
because the measurement here is impacting the local phase. And what determines which way the excitation goes at the end is the relative phase at that beam splitter. So one way to change the relative phase between two things is just to change a local phase. And so this model I just described to you is totally local. If, however, you decided, no, I really insist on thinking of this as a particle, then you have to contend with non-locality. Because if you say, look, there's a particle and it has some, say, internal phase. So if I go and I measure and I don't find the particle here, and I try to randomize the phase, I now have to say, well, I have to randomize the phase up here, like on the particle on the other side, because that's where the phase lives. And that would have to be non-local. But if you say, no, each mode has some internal degrees of freedom, they each have a local phase, and it's that pair of phases that determines how things, which way the excitation goes eventually, then I don't need any non-locality.
So the state is described by a pair of phases.
That's right. Every mode in this Mach-Zehnder, so there's two of them, each one has this binary phase, 0 or pi. Each one is occupied or unoccupied. And so it's a 16 state space. There's 4 states for this guy, 4 states for this guy, 16 in all. And the story is that I can randomize the phase down here and thereby destroy interference. No non-locality required.
But so it's a local hidden variable model,
yes,
which is entirely consistent with everything we know about quantum mechanics, all measurements we...
No, it's not at all. It's consistent with this very specific aspect of the phenomenology of interference. So the point of this hidden variable model is certainly not to say this is an interpretation that'll work for all of quantum theory. It's more to say it's a challenge to the notion that the mystery of quantum theory is this wave-particle duality in the sense of how can you possibly explain the fact that you get interference when you don't measure, but then when you measure, interference goes away? How can a classical picture explain that? This hidden variable model is meant to show that actually, yes, you can explain that in a classical model. Here's how to do it. Don't use particles, use modes and their local degrees of freedom. And so it's just saying that phenomenology can be explained with an underlying classical theory. But then we go on in other papers to show, but there are other aspects of the phenomenology that can't be explained. And that's what we should have been focused on. When people say, what's the mystery of quantum mechanics? It should not have been this story about wave-particle duality. It should have been these more nuanced features, which really cannot be explained. So like the broader theme here is what we try to advocate for is to follow in John Bell's footsteps. So John Bell had this nice no-go theorem. And so the methodology of no-go theorems in quantum foundations, I would say, is set down a bunch of assumptions and then derive the contradiction with the operational predictions of quantum theory. And that's what was not done in the case of interference. Many people in history have said, you can't explain this classically, but they didn't back it up with a no-go theorem. They didn't say, if you subscribe to these principles of classical theories, you will get a contradiction with the predictions. That's what made room for the possibility of this kind of hidden variable model I just described. Whereas if instead you say, here are all my assumptions, I get a contradiction with quantum theory, then everybody who looks at that has to say, right, which of the assumptions do I want to give up in my interpretation? And that's a better way to proceed, because then at least we're sort of focused on the phenomenology that really is difficult to explain. We might have disagreements about how we should encode classicality in our assumptions, but at least we can have a conversation about that. We can say, oh, your assumption 2 is the one I disagree with. Let's talk about whether that's the right way of thinking about a classical theory. Whereas if we just make pronouncements about, oh, you really can't explain this without backing it up with a no-go theorem, that's detrimental to progress, I would say.
So then when someone says this is a classical theory, or this theory is quantum mechanical, what's at its core, what does that mean? So when you say a theory is classical, what do you mean? Okay.
Well, first off, I would say, in my list of what are the main activities in quantum foundations, I said one of them is trying to understand sort of what's innovative about quantum theory relative to the classical theories that came before. And I think there's, again, a bit of an illusion that we all agree on that. That really we don't. That the question of what is classical and what is not classical really varies from researcher to researcher. It has a lot to do with what your interpretation is. So if you believe in the many worlds interpretation of Everett, you'll have a very different answer to that question than if you believe in the de Broglie-Bohm theory, or if you think there's a research program called Quantum Logic, which tries to say that the real innovation of quantum theory is to logic and not to physics at all.
Do you mind if I pause you for a sec?
Sure.
So people really talk about different interpretations as though they're mathematically equivalent. That's sort of like, for people who aren't in foundations, this is sort of the underlying current. But you're saying this is in some sense not the case, that you really can, from different interpretations, the different interpretations do have different mathematical outcomes.
Well, what I would say is some interpretations, we could already say today what sorts of experiments, were we able to do them, would be able to adjudicate between that interpretation and alternatives. So the collapse theories make different experimental predictions, and there's a challenge to go and test that. But what I would say more is that the way you, for instance, decide whether something should be judged, non-classical or not, depends on your interpretation. And so in particular, let's say I'm trying to build an architecture for a quantum computer, and I want to benchmark it. I want to say, oh, is this thing that I've built doing anything that could not be done by a classical computer? Well, now it's important. Well, how are you defining classicality? What is the benchmark? What do you have to show to demonstrate that this couldn't have been simulated? So complexity theory is sort of one angle on that. But another angle is to have a notion of classicality and to try to defend it and show that it's coherent, and then judge relative to that. So I think different interpretations might can disagree about what counts as proof of non-classicality, proof that there's something puzzling or novel going on here. That's the sense in which I meant it. And yeah, I would say something like all interpretations, all approaches and research programs, there's a nugget of weirdness, there's a nugget of innovation in quantum theory, and it's kind of like a ball under the carpet. You can push it around, but you can't make it go away, and people disagree about where it is. So for some people, that nugget of weirdness might be, they try to confine it to, it's the nature of logic. That, in classical logic, a conjunction of the AND operation distributes over the OR operation, but that fails in quantum theory. And then others will say, oh no, it's about the locality. That the key thing is that quantum theory doesn't satisfy locality. For Everett, it's, things that you thought were merely alternatives, possibilities, they're all actual. They're all happening in parallel. So there's all these places you can put the innovation, and it impacts what people are going to say is classical or non-classical. Okay, so you asked, well, what do I think should be called classical, non-classical? So it's tied to this idea that we should think of wave functions and quantum states as being descriptions of our knowledge, so the incomplete knowledge we have. So the way I like to think about it, is that one of the fundamental distinctions of any realist interpretation is between sort of what is and what we know. And you can think of that as also kind of the causal structure, sort of what causes what, and the inferential structure, what can I infer from this knowledge? So I like to use frameworks for describing physical theories where that omelet is unscrambled. It's very clear, like what's about causation, what's about inference. And so if you say, well, what does a classical causal theory look like? I would say at the most abstract level, it's classical theories can have lots of different degrees of freedom in them. They could be discrete, like a cellular automata. They could be particles moving. They could be fields. They could be lots of things. But what they all have in common is that it's essentially a kind of set of possibilities. The kinematics, or the set of possibilities for the physical state at a given time, is given by a set. And the dynamics, how things evolve, is some function over the set, right? If I say, well, how have things changed? There's just some function. So you can describe it very abstractly as sort of like it's committed to sort of sets and functions, and I can figure out what causes what just by asking, like, okay, if there's a variable here and it functionally depends on a bunch of variables earlier, which ones does it depend non-trivially on? Those are the ones that are causes of it, and other variables that it doesn't depend on at all are not causes, right? So you can sort of work out causal connections that way. And then on the inferential side, you have Boolean propositional logic, you have Bayesian probability theory. These are things you can say, oh, here's what I know about where I am in that set. Here's what I know about which function is applied. And those formalisms gives me a way of propagating my beliefs. If I know something about the initial time and I know something about what functions are applied, I can deduce what do I know about where I am at the next time. So all of that is part of my notion of a kind of classical theory at a very abstract level. And then to that, I add some kind of principles. And for me, the main principle that I think all theories, whether classical or non-classical, should abide by, and therefore which sort of constrains what I'm willing to call classically explainable, is a principle that Einstein made a lot of use of, but I think ultimately goes back to Leibniz. So this is the philosopher who co-invented calculus with Newton. So he had this thing called the principle of the identity of indiscernibles. And he had his famous correspondence with Samuel Clarke, who was basically a spokesperson for Newton. So basically it's a correspondence between Newton and Leibniz. So in philosophy of science, you hear a lot about this. And he talked about his complaints about the Newtonian worldview. And it basically boiled down to a violation of a certain principle. So Leibniz thought, if there were such a thing as absolute space, as Newton has it, and particles that live in it, then if you move all the particles over in absolute space, nothing in what you observe could possibly change. And he says that's a problem, that if there's some change in the physical state of affairs according to your worldview, but no change in what I could observe. So if you have ontological non-identity, but empirical indistinguishability, then it violates the principle, right? Like every ontological distinction should be in principle observable somehow, right? So if you imagine two scenarios that you think are physically distinct, there should be some way in principle that we could see that. And so he wants to say, yeah, if you bring me a theory and there are these distinct possibilities that I cannot in principle distinguish, let's throw that theory out and replace it with one that doesn't have that feature. And so he argued that you should dispense with absolute space in Newton's theory and just talk about the distances between the particles, that should be the only real thing in Newtonian mechanics. But that principle I'll call it, Leibniz's principle. It's was used by Einstein very successfully. So his work, if you look at the beginning of his paper on special relativity, he basically points out that in kind of ether theories, if you have a kind of loop of metal and a bar magnet, and you imagine that the loop of metal is fixed relative to the ether and the bar magnet moves through it, that's one picture of what's going on. And now here's a totally different physical situation. It's the bar magnet that's at rest with respect to the ether and the loop that's moving over it. And he says, okay, according to these ether theories, these are very different physical scenarios, and the explanation of the current induced in the loop is very different in the two cases. In one case, what you have is a time-varying magnetic field. In the other case, you have a static magnetic field, but you have an electron that's sort of moving along, and it's feeling a force by virtue of moving through this magnetic field. So the way you think about what happens is very different. But he says, but look, the empirical signature is exactly the same. I get exactly the same current. And so, he says, like, he doesn't mention Leibniz explicitly, but he says, what we would prefer is a model where the only thing that's relevant is the relative the only thing that's relevant to what we observe is the relative motion. So we shouldn't have a theory wherein there's this extra fact about what your motion is relative to absolute space, or the ether. Anyway, so Einstein uses this principle also in the equivalence principle, like the idea that if you're in an elevator with no windows, you can't tell whether you're at rest in a gravitational field or accelerating through free space. Nothing you observe tells the difference. He says any model like Newtonian gravity that says nonetheless there's some physical difference between these two scenarios, we should get rid of it and replace it with one that says no, they're the same. And that's what general relativity does. It says, it's the curvature of space-time that determines what I see in the lab, in this elevator, and they're the same in those two scenarios. Anyhow, so in my studies in the foundations of quantum mechanics, I found Leibniz's principle to be effectively what vindicates something called non-contextuality. We don't need to talk about that, but there's this nice principle of non-contextuality. But ultimately, I think it's just an application of Leibniz's principle. And so for me, what's a classical explanation? In an old language, I'd say, it's a non-contextual hidden variable model. But more refined would be it's a description that sort of separates out causation and inference, in this framework of sets and functions. But furthermore, it abides by this Leibnizian principle, namely that if you have two situations that you think are distinct, right? I either have different physical things going on, different causal structures, or different knowledge about them, then that should translate into some in-principle distinction on what we can observe. So very long answer to your question, but that's for me, that's classicality. It abides by Leibniz's principle, and it's essentially one of these hidden variable models, for example, that distinguishes causation and inference.
And on the other end, a quantum model, what breaks there?
Well, so if you have some data, some statistics, some correlations you've observed, and then you can prove that no model of the type I just described, one that sort of involves sets and functions and Bayesian probability theory, and this Leibnizian principle, no model like that can reproduce those correlations. Then you can say, I have a no-go theorem, and I can say no classical Leibnizian explanation of this experiment is allowed. And so for me, that's the witness of non-classicality.
I see. So it's based off no-go theorems in principle. So
right.
I come up with an experiment that says there is no classical system that could perform this. I see it in an experiment. That's a quantum effect.
That's right. That's right. Yeah. So like in your interference example, what we are able to show is that this fact that you can toggle between seeing interference and destroying interference when you look at the which way information, that doesn't pose any challenge to having one of these Leibnizian models. Like we provided one. But what we then showed is that if you look at the transition between those two extremes, so when people study interference, they sometimes look at the trade-off that exists between fringe visibility, so not perfect interference, but you're going from sort of having perfect interference to no interference at all. There's sort of a measure of that, which they call fringe visibility, and some measure of how much information you got about whether it was on this path or this path. So let's call that path distinguishability. So in quantum mechanics, if you plot fringe visibility versus path distinguishability, you get a kind of a particular curve. It's not linear, but it's a section of a circle essentially. And so what we were able to show is that if you have one of these Leibnizian classical models, or in other words, a non-contextual hidden variable model, it would have been a linear trade-off. So the endpoints are the same, perfect interference or perfect which-way distinguishability. And the stuff in between is what is the witness of the non-classicality, the fact that it trades off in this one way rather than another. So that this is a lot of my research program, is to go back to a lot of the sort of typical examples people provide of phenomena that is thought to be difficult to explain classically, and ask, is it really difficult to explain classically? Can I prove a no-go theorem? Can I show that no Leibnizian classical model of the type I described can explain this? And if it turns out you can, then go looking for a more nuanced feature of that phenomenology which you can't explain. So sort of we do this for various phenomena. Interference is just one of them, but I've looked at the nature of uncertainty relations, or the nature of discriminating non-orthogonal quantum states, which is just a problem that quantum information theorists are interested in. And so you can kind of go across the board, or look at something called the no-cloning theorem. You can show that, that the existence of a no-cloning theorem, the fact that you cannot make copies of a quantum state, actually you can make sense of that within one of these classical Leibnizian models. But more nuanced aspects of that, in things like, what's the probability that you can get an imperfect clone, or things like that. More nuanced aspects of that you can prove do not admit of a classical explanation. So the way I like to think of it is the project is kind of deflationary. It says a lot of the things that you've heard are on the list of mysterious quantum stuff. They're not. They're on the list of things that we could do justice to, if only we think of the quantum state as being more like a probability distribution, as being a description of our knowledge. Then just imagining an underlying classical theory works just fine. But there are still some phenomena, more nuanced aspects of what we see in quantum theory that can't be explained in that way. And so we sort of need to populate that list so that we know what to focus on. What's the real challenge of making sense of quantum mechanics? It's this list. And what you find when you do this is that the set of things that are hard to explain classically is much smaller. Generally, it's more quantitative. It's like, this linear trade-off versus a nonlinear trade-off. So if I look at sort of the height of that curve, there's a little gap between what I could achieve with the linear and what I can achieve with the curve. And that gap is the quantumness. And if I have too much noise in my experiment, then maybe I can't see that small gap. And it's the same with Bell inequalities
which hopefully we'll get to in a little bit.
Maybe we'll get to Bell inequalities. Is like, there's a small gap between what you can get in a truly quantum experiment and what you would get if it had a classical theory underlying it. And so I like to think of this as sort of the thin film of quantumness, that like our new picture shouldn't be like, everything in quantum mechanics is mysterious, but rather, no, most of it makes sense from a classical worldview. And then there's this thin film of more nuanced stuff, which is where the real challenge lies. And so right now, I spend a lot of time trying to figure out what exactly is in that thin film of phenomena that are difficult to explain.
So I have a list here that I was going to ask you about. So interference, wave-particle duality, entanglement, non-commutativity, interference, collapse, no cloning, teleportation, no steering, and so on.
Yeah.
What would you say is, do you have a small list that's easy to explain or describe, which is in this thin film of...
Well, so everything on that list, it kind of depends what you mean. But take one example. I think you had non-commutativity on the list, right? So say you cache that out and saying, I just mean the following. I mean that for certain pairs of measurements, if I do the first measurement and then the second, I'll get a different result from if I had just done the second measurement without having done the first, right? That somehow this first kind of randomizes the outcome of the second. So if you say, take just that basic phenomenology, right? So no more details than that, right? And typically people do say that is the essence of non-commutativity. Even that is sort of what we should say is hard to explain classically. I would say no, it isn't truly quantum, because I can come up with classical Leibnizian, theories that have exactly that feature. And the way they work typically is that, when you, if I have a system that has two binary degrees of freedom, like we talked about earlier, so it has, let's call them, they're analogs of, in quantum mechanics, what would be X spin and Z spin. So these are two properties that a quantum system can have. So in my model, I say, okay, X spin has one of two values, plus or minus 1, and so does Z spin. And it has both those values at the same time. But it so happens that when you try to measure one, you randomize the other. So in that circumstance, if I try to measure z-spin, I might be able to have a preparation that makes the z-spin outcome perfectly predictable. I'm always going to get +1 for this preparation. But if I come in with an x-spin measurement, I can randomize the z-spin property by virtue of it. But I still have an explanation of what's happening in terms of this underlying classical theory. It's just that measurements sometimes disturb. So I have to sort of allow that a measurement can disturb something about the physical state. And I can explain that case. But if you go to something more nuanced and you say, oh, well, non-commutativity also has a kind of quantitative aspect. So, how, for a given amount of information I learn, so I could take that intermediate measurement and I could dial down its informativeness, right? So there's ways of sort of adding noise to it such that it teaches me less about the x-spin. I could dial it all the way down to it teaches me nothing. So now I'm back to like not doing it at all. So I can say, all right, as I change the informativeness of that first measurement, and I look at how that trades off against the predictability of the second measurement, what does that trade-off look like? So I can draw that out, and quantum mechanics predicts a particular curve. And then I can ask, well, can that curve be explained in one of these Leibnizian classical models? And what you'll see is that, oh, no, it can't, right? That curve would look different if it had it. And so there is an aspect of non-commutativity that is sort of truly quantum. It's just not the aspect that we tend to typically focus on. And so that's sort of the thin film is the sort of this more nuanced aspect of non-commutativity.
So if I was to ask you, is interference classical or quantum, your response in some sense would have to be in what context, almost? Yeah,
like which aspects of the operational phenomenology of interference are you talking about? And if you came back with, oh, just the very fact that if you try to measure which way information you destroy the interference pattern, I would say, oh no, that doesn't require me to have any innovation relative to classical theories. It's not truly quantum. Whereas if you said, oh, I mean the very particular functional trade-off between how much fringe visibility you have and how much information about which path you have, I would say, yes, that aspect of interference does witness quantumness. So yeah, just the one word interference kind of doesn't tell me which one you're talking about. But in most conversations, it's the very basic qualitative phenomenology that people are talking about. And generally, my answer there is that, yeah, those things don't actually pose problems to having a classical Leibnizian model.
So you described, you had sort of this image that the quantumness of a quantum theory is sort of this ball under the carpet.
Yeah.
So it's this small thing that you sort of can't get rid of.
Well, yeah, and then sort of where the ball is kind of like the
Depends
different
on your
interpretational camp. Yeah, so like different people, like some people say, oh, we're going to put it under logic, and others are going to say, oh no, we're going to put it in the way causation works, for example.
Do you have some idea of, regardless of what interpretation you're taking, do you have some idea of how much of a quantum mechanical theory can be described classically? In other words, how thin is the thin film of?
Yeah, I mean, if you...
That's a difficult question to answer.
Sure. I mean, I often I'm kind of fighting this uphill battle, trying to, because like my view is a minority view, I'm trying to persuade people who have a long list of qualitative phenomenology, and they want to say that phenomenology is intrinsically quantum, and I want to try to persuade them that's not right. So the counting I like to use is sort of how many phenomena, right? So I like sometimes, as you know, because you were a Sci student, Sci students do essay projects when they're here at Perimeter, and so I will sometimes ask a Sci student, please make me a list of all the things that you think are intrinsically quantum, and I'll see how many of them I can explain to you using one of these classical Leibnizian models. And if you sort of measure things that way, right? So like your list, non-commutativity, no cloning theorem, interference, these sorts of things. And by those you mean the sort of basic qualitative phenomenology, I would say, yeah, most of those can admit of a classical Leibnizian model. And so the thin film is thin relative to the counting of a list of phenomena. I mean, if you tried to quantify it in a different way, like you might, for instance, look at things like Bell inequalities and other kinds of inequalities, where you might want to say, oh, how big is the area or the interval that can only be explained quantum mechanically versus the interval that can also be explained classically? That would be a different way of measuring it. But I think that's less interesting. Like I like to sort of look at lists of phenomena and say, how much of those are really challenges to the classical worldview? And my impression is that most such lists will be on the side of, oh, actually, this can be explained classically. But there will be standouts, like when people talk about Bell's theorem and Bell inequality violations. I'm not saying that that's on the list of things that are easy to explain classically. No, that's on the list of things that are genuinely quantum. And it's the same thing with the quotient, something called the quotient-Specker theorem. So there's this notion of non-contextuality. You can derive inequalities that delimit what can be explained non-contextuality, what not. And that coincides very much with my notion of a classical Leibnizian model. So if you have an experiment that violates these non-contextuality inequalities, that will definitely be on the side of truly quantum. And I would say advantages in quantum computing, those are also on the side of many of them are on the side of truly quantum. So that there are things on this list, and from my perspective, sort of we need to try to add as much as possible to that list, so that we're in the best position possible to understand what's like the right way to think about this theory. Because now we're focused on the right phenomena, the one that are truly challenging to explain.
I wanted to ask you next, how does classical physics emerge from a quantum theory? But now that you've sort of described the weirdness of quantum mechanics as this thin film,
right,
it sounds much less amazing that we can derive a quantum world, classical world rather.
Yeah, I think the kind of I think in some interpretations that coming up with the classical world as a kind of special case of a quantum world, maybe is a challenge or something that requires a lot of work. And in other interpretations, maybe it's not such a big deal. I can say in this sort of research program, and I guess we didn't discuss this explicitly, but what I'm describing for you is a research program. It's not a interpretation that I have on the table to offer. It's more like I think that this is the right way of thinking about quantum mechanics, and we should take on board this idea that quantum states are states of knowledge and see if we can make sense of the formalism and unscramble the omelet. But I don't have an interpretation on offer. I just don't think that any of the interpretations that are on the table are adequate.
What would make an adequate interpretation? What is your checklist?
Yeah, okay, so, what makes a good scientific theory? Generally, I would say, what will happen when we get a rough consensus about the correct interpretation of quantum theory, I think, is that the sign of a good scientific theory is that it's very internally coherent and it makes everything fit very well together. So, not just the experimental evidence, but a bunch of theoretical notions. If it's all sort of mutually supporting, very coherent, that tends to be evidence in favor of this is the right solution. But also, it generally gives you sort of tools for thinking that lead you to ask interesting new questions that you hadn't thought to ask before, and it sort of leads to rapid development. So it's sort of it becomes a progressive research program. When you've got something right, it usually means you can do something with it and go somewhere. And it helps us achieve our pragmatic aims. So if I want to build a quantum computer and I've got the correct interpretation, generally I'll be able to do that better. I'll be able to have better intuitions about what sorts of computational tasks have a quantum advantage, for example. So I think all of those kinds of things will sort of tell us that that's right. Now, from my own perspective, I have a kind of checklist of what do I think are good starting points, good assumptions to make to build towards that. And so for me, Leibniz's principle that I mentioned earlier is, I think that's really at the core of what I believe. And the only way to really get a Leibnizian interpretation of the formalism is to take the quantum state to describe our incomplete knowledge. But roughly, I can tell you sort of what the research program looks like. The idea here is that in quantum theory, the innovation is really in the kind of theory of causation, so what causes what, how that all works, and the theory of inference. So I said classically the theory of causation is basically sets and functions. The theory of inference is Bayesian probability theory, and there's this algorithm involving Bayes' theorem and all the things, how you propagate your knowledge. And the idea is that both those things are not quite right and they need to be modified. And so it's not going to be sets and functions that describe causation, and it's not going to be Bayesian probability theory that describes inference, but there's still a huge number of constraints. So all the usual concepts about causation, should go through. Causal influences should be mediated, for example, and there's a particular facts about inference should not be violated. Like if A and B teach me nothing about C, then A alone is not going to teach me something about C. Things like that. And the way they interplay has to fit together. So, if learning about one system causes me to update my knowledge about the other by virtue of them having a common cause, right? So take the classical case. Well, that means that I can sort of update my knowledge about this guy by sort of first saying, well, what I learned about him taught me something about their common cause, which is why I updated my knowledge about this guy. So that should hold true in a quantum theory of causation inference as well, that any kind of inferences I make about this system based on this system, when there's a common cause, it should be possible to make those inferences in a stepwise fashion. And if somebody comes to me with a proposal that doesn't have that feature, I will say, well, that's not what I'm looking for, right? It doesn't, the interplay between inference and causation in that model is not right. So that's the kind of picture. And sometimes I hear sort of objections to this on the grounds that, there's certain facts about realism that are kind of sacrosanct and they're analytic, like they're true by definition, that it has to be sets and functions, because that's what we mean by reality. To which I respond that I don't think that's the way physics works. I think like we can't have kind of conceptual dogmatism. We need to allow flexibility in our concepts. Like if I think in 1905, Einstein was trying to derive the Lorentz transformations, and he found a way of doing it ultimately, in terms of these simple principles, relativity principle, that the laws of physics are the same at all reference frames, and the light postulate, that the speed of light is independent of the speed of source. Now, if somebody, suppose in an alternative history, before Einstein did that work, somebody came up with a no-go theorem. And their axioms were relativity principle, light postulate, and the conventional notions of space and time. And they said, look, these three things lead to a contradiction. And now if Einstein had come along and said, it's the conventional notions of space and time that have to go, that's the assumption that's wrong. For them to say, well, but that's just what we mean by space and time. You can't change the meaning of space and time. That would be inappropriate. That would be like conceptual dogmatism. And you're saying like, oh no, I get to decide what space and time mean. No, the kind of most coherent notions of space and time are the one that sort of make sense as broadly as possible. And so what Einstein realized is that, okay, those conventional notions have to go. The notion of absolute simultaneity no longer holds. Our old notions of space and time do get recovered as kind of approximations in certain cases where, velocities are low. But, the key step was saying, the meanings of things like space and time are not given a priori, they're not fixed, they're not constraints on us, they're allowed to be flexible. And it was the same thing with non-Euclidean geometry, like the real breakthrough. So this is the geometry that, superseded Euclid's geometry. And the breakthrough there was that people said points and lines, we have this kind of intuitive notion of them, but actually I can write down axioms in a mathematical system that have the terms points and lines in them and allow the interpretation of those terms to emerge at the end. Like, what makes sense from this set of axioms? And then what you find is that some of your intuitive notions of points and lines don't hold anymore. So you're letting the notions of points and lines kind of take on their meaning as a result of the set of axioms they're embedded in. And so the project here is to say quantum theory is about causation, it's about inference, but the meaning of causation and inference, that's something that's going to emerge when we figure it all out, and there's constraints on it. But the quantum notions of causation and inference are still going to be recognizably about causation and inference, just like space and time and relativistic theories are recognizably still space and time, but they're going to be different from the classical notions. And that's what I think the right interpretation is going to look like. That's where the innovation is going to happen.
You've mentioned now several times no-go theorems.
Okay.
So I think we should touch on them before, before going further. So are you able to give, and also I'm interested in a little bit of historical context as well. So what is Bell's theorem, and why is it important, and why is it one of the main tools that's used by people in quantum foundations?
Right. So Bell wrote this paper in 1964, which is the first reference people typically point to, as that's where Bell's theorem was first proven. He was working on the question of how to interpret quantum theory, and he studied David Bohm's paper on how to come up with a realist interpretation of quantum theory. He noticed that in that theory you had these non-local influences. And he started wondering whether every hidden variable model would have to have that feature. or every hidden variable model satisfying certain background assumptions would have to have that feature. And that's ultimately what his theorem showed, that it's a list of assumptions, and then roughly speaking, embodying the kind of classical theory we talked about earlier. So it assumes that the fundamental physical states are given by a set, and dynamics are given by functions, and our knowledge of these things are Bayesian probability theory. It assumes all that. And then it says, can you possibly explain the kinds of correlations we see in certain experiments that involve a common cause? And it shows that quantum theory predicts correlations that you can't explain in this way. And so one response to that would be to say, aha, it was the locality assumption that was problematic, that there must be these influences that go between the two wings of the experiment. That's one assumption of, you can think of it, he's got this list of assumptions, it derives a contradiction, you have to give up on one or more of them.
What are the assumptions there?
Well, so what you have in a Bell experiment is a device that prepares a pair of systems that then go off to two labs. So that's the source. And then in each lab, you're doing one of many measurements. So it's enough to imagine you're doing two possible measurements. So you can think of it as you have a setting variable that determines which measurement you're doing, and then you have an outcome variable, which is just the outcome of the measurement. And again, that could be binary. You could have just two values. So over here, you have a setting variable and an outcome, and then on the other side, it's the same thing. You have a setting variable and an outcome. And so your data comes in the form of the relative frequencies of the different possible outcomes for each of the four possible settings. And then you ask, is there any probability distribution over the physical states of this pair of particles, and ways of modeling these measurements as just responding to the physical states of those particles, such that I can generate those distributions? And that's where the answer comes back, no. There's certain patterns of correlations you can't explain this way. And I could try to make it evident. I don't know if it's worthwhile, but I could give an example of those patterns. It just takes a bit of time.
What does the example look like? So is it...
You could think of it as a game that like the game would be something like the particles are gonna have to answer the question that the measurement device poses to them. And each particle is gonna see one of two questions. And the idea is that, can the particles sort of agree with one another ahead of time what answers they're going to give to these questions, such that they can be prepared to kind of win the game. And winning the game is something like, if you're asked the same question, then your answers should agree, or if you're asked different questions, your answers should disagree. The particles don't get to communicate to one another what question they've got. They just have to have some scheme ahead of time.
So that's plan. The hidden variable.
Right. And so what you can show is that if I set up the following game, which is that, right, so imagine the setting variables are either 0 or 1. So you say, look, if both the setting variables are 1, your answers should disagree. The outcomes the particles give should disagree. They should be different. So the left particle gives outcome 0, the right particle gives outcome 1, or 1, 0. But in all the other cases, so if the two settings are 0 and 0, or 0 and 1, or 1 and 0, their answers should agree. Both 0, both 1.
And you have to do as well as possible.
Yeah, and let's say you try to do this 100% of the time, like no matter what questions you get posed, imagine you always have to win the game. You can show that no matter how the particles prepare, they can't win the game. There's no scheme that allows them to win that game, because basically you sort of need to know something about the other setting. And then quantum mechanics tells you that if you work out how frequently do you expect to win the game, if you do have this sort of classical model, the answer is 75% of the time. Quantum mechanics allows you to win it 85% of the time. And so that's the thin film, the gap. So the 75% is like an inequality, like your probability of winning the game should be less than or equal to 75%. The fact that quantum theory predicts you can get up to 85% is a violation of that inequality. And so Bell's theorem is that possibility of violating one of these inequalities. So yeah, Bell's theorem is that result. It leads to people kind of debating which assumptions of the theorem should be given up. And many people say, oh, it's the locality assumption. So many people see this as a proof of non-locality in quantum theory. I don't see it that way, and others don't see it that way, who might not agree with me. They might see it as some other assumption different from the one that I see. But what's great about Bell's theorem is that it kind of started this better methodology, I would say, for thinking about the foundations of quantum mechanics. Rather than saying, I think what's mysterious about quantum mechanics is X, Y, Z, because I can't think of any way that this would make sense in classical theory. People say, here are the assumptions that I'm making. I'm going to try to articulate them as clearly as possible. There might be some background assumptions I haven't articulated properly, but I'm going to try my best to articulate what I'm assuming. And then I'm going to prove rigorously that this contradicts the predictions of quantum theory. And that's a great starting point, because now we can have a discussion. Like if I say, well, obviously we both want to avoid a contradiction. I think it was your assumption 3 that was invalid. And now we can get into the details of assumption 3, and we can argue about assumption 3, and can we refine it and make it more palatable to me? Could you prove a no-go theorem that I'm still happy with, even though you've refined assumption 3 to something that I'm happy with now? Oh, now I feel the tension. Like, I thought that the problem was with assumption 3, but now that you've fixed it, I realize that that's not a way out. I have to think harder about the way out. And so Bell's theorem has played such an incredible role, because it's, physicists generally do want to preserve locality. So it's part of relativity theory is the idea that causal influences should not propagate faster than the speed of light. And if you think that the solution to Bell's theorem is that there's a causal influence between the wings, there are ways of doing the experiment that force that causal influence to have to be faster than the speed of light. And so you get this tension with relativity. And so I think all physicists feel that tension, and many of them are reluctant to abandon that part of relativity. So they want to see a way out of the contradiction. And so it is a great challenge to making sense of quantum theory. Can you salvage locality within quantum theory? And people who advocate the Everett interpretation, one of the things that they like about the Everett interpretation is that they see it as a way of preserving locality. Unlike, for example, the Bohm-de Broglie approach, which jettisons locality. So more generally, I think what's great about no-go theorems is that they sort of focus our attention on the assumptions, like assuming the logic of the theorem is sound, and we all agree, okay, the theorem's fine. It focuses our attention on the assumptions, the principles. It leads us to refine those principles, clarify our thoughts on notions of causality, notions of locality, inference, all those things. And that's how we really get conceptual progress. So I'm a big advocate of that approach.
So in my mind, I had always thought, and maybe I need to go back and read over things again. So I had always thought that the outcome of that experiment was that local hidden variable models were ruled out. But right. So you're interested in the wave function being a state of knowledge, which sort of aligns with there being hidden variables.
Sure. So how do I? You're absolutely right that the way it's usually sold is, local hidden variable models are ruled out. Sometimes, rarely it gets sold inappropriately as hidden variable models are ruled out without the locality in there. But you're right that most of the time it's local hidden variable models, and there's some truth to that. But even there's ways of sort of salvaging a, what I would call a classical Leibnizian hidden variable model without giving up locality. So there's something called superdeterminism, where it says, actually those setting variables it was not possible to freely choose them. They were actually kind of common cause related to the source, the pair of particles. And so there's ways of generating violations of the Bell inequalities through that mechanism.
So your wave function in some sense includes the apparatus in that case?
Well, in this case, you're coming up with this deeper model, which doesn't have wave functions in it per se. It's sort of like simulating the wave function. But you're violating a different assumption on Bell's list of assumptions, namely that I can think of the setting variables as having been, being statistically independent of the source of the particles. So they say, hey, that's an assumption. I could give that up. Yeah. And personally,
so are you a proponent of?
No. I am not a proponent of superdeterminism, this particular approach. But it's an example of a way you could try to salvage locality by giving up a different assumption of Bell's argument. Personally, I would say it's the framework of hidden variable theories, or sort of the kind of framework in which we, describe the deeper reality. That's what I think has to be given up. So, the way I like to think of that framework is it's got an aspect that's about causation, an aspect that's about inference. In this sort of classical Leibnizian picture, it's like sets and functions and Bayesian probability theory. And what I want to say is like that has to change. So it's no longer sets and functions. It's no longer Bayesian probability theory. It's something different. It's still going to be recognizably about causation and inference, but it's going to be more exotic. And I'm still going to be able to talk about kind of realism because correlations will still have causal explanations in that framework. So it'll still be the case that when I have correlations between these two things, it's by virtue of them being common cause connected and not by virtue of a superluminal influence. So in that sense, I hope to preserve locality, right? No superluminal influences, only common cause explanations. But if you ask, what parts of Bell's assumptions are being given up, the answer is really the framework in which it's all embedded. The idea that, this hidden thing is a variable. It takes one of a set of values. That's a set. And how does it determine the outcomes? Via some deterministic function. And how do I describe my incomplete knowledge of it? Via a probability distribution. Like those aspects are all part of the background assumptions.
So so I'll sort of parrot back what you just said to me, and you can tell me, because just so I understand properly. So you're proposing, in some sense, a model that's almost classical in the sense that it has hidden variables, and which is completely local. The locality has nothing to do with classicality, but it's classical in the sense that you have hidden variables that you can follow through time. But what you're changing is in some sense the statistics, the way that you're doing the probabilities on these objects as they're propagating through space and time. Is that?
It's close. To my mind, when we talk about hidden variables, like the word variable to me sounds very much like a commitment to the physical state space being a set, and a variable can take any value. So I want to kind of drop that.
What do you replace the set with?
Well, I don't know yet because it's a research program. But if you think about sort of a causal theory, wherein you have sort of these, say, different systems, and every one of them can be thought of as a variable that ranges over a set of values. So you got a bunch of sets. The possible physical states of the collection is just the tuples of values from each of these sets, and dynamics is functions. What I said before about causal connection, whatever, if this variable here is a non-trivial function of these guys, I'll say that there's a causal connection. Now, if you say, can I preserve any of that business about causal connections without having sets? Yes, I can. So for example, if I just look at the formalism of quantum theory, I can sort of identify with each system this mathematical object called a Hilbert space. And I don't need to pick out a particular ray in Hilbert space. I can just say the Hilbert space. And then I can look at the dynamics. And there's these things called unitary operators that describe the dynamics of a multipartite system to some other multipartite system. And I can answer questions like, does this output here depend causally on certain inputs? Without ever having to stipulate that these are sets and this is a function. I have a way of talking about where there are non-trivial causal connections without necessarily having sets and functions. So that's the kind of idea that, there's a more abstract way of describing this in terms of a mathematical framework called category theory. So your sets would be like your objects in the category, and your functions would be the morphisms. But there are other categories where the objects and the morphisms are not sets and functions, but they still might have a lot of the same structure that any causal theory ought to have. Every causal influence is mediated, things like that. So that's the sort of idea that there's something more abstract, not sets and functions, and therefore not abiding by what we usually think of as a hidden variable theory, but still a lot of the features of a causal theory that you would want to have of a causal theory. And then when you ask, what do I know about those systems? You can't now say, my knowledge is going to be what element of the set is true, right? Like classically, that's how we do it. But I could still say, I have a certain knowledge, and that knowledge has relevance in the sense that as I propagate it through the causal structure, it teaches me things about other systems. And ultimately, I will, in this formalism, you will need to make connection with the outcomes of experiments, which can be thought of as classical variables. So at the end of the day, you are going to be computing relative frequencies of certain events. You're going to have to interface with classical probability theory. So you're going to have to recover Bayesian probability theory in a certain limit. But kind of in the middle of your inference between these classical variables and these classical variables, there's a bunch of quantum variables. And I should be able to update my knowledge there. And the formalism I'm going to use to do that is not the standard formalism of hidden variable models with Bayesian probability theory, but this more exotic alternative.
It's kind of interesting. I'd never really thought about this deeply, but so anytime you have a no-go theorem, obviously it comes with a set of input assumptions.
Yep.
And so the theories that you're looking at are in some sense amorphous, because you can remove one assumption or you can play around with the assumptions, then you get different theories. And so the program is actually very large, because there's just a large space of you can look in a lot of different areas. And so at some point you have to make decisions about where you sort of hammer down the fabric.
Yeah. Like, like even if we look at this small microcosm of, oh, I want to think of quantum theory as involving some innovation to causation and inference. It's kind of unclear what's the essence of causation. Like what parts of causation do I really kind of not want to give up? And were I to give them up, I would say, oh, it's not really a theory of causation anymore at all. That's kind of up for grabs. Like, you know, I might have some part of causation. I think anything that doesn't satisfy this is not really a theory of causation. I could be wrong about that. And when somebody else figures it all out and they come to me and they say, oh, look, I gave up on the thing you were unwilling to give up. And here's why, let me persuade you that still, I might say like, yeah, you're right. I was wrong to think that that was kind of a sacrosanct aspect of causation. But I see that your approach has like kept, you know, everything else and it all makes sense as causation. And now I realize why I was misled into thinking that was key. So it is this, you don't know exactly what you need to hold on to and what you need to give up. I mean, I start with some strong intuitions and see where you can go with that. And as long as nobody has proven a no-go theorem that starts with the assumptions that you're holding on to and proves a contradiction, you know, there's room to make progress. Yeah, no.
And so I'm going to pronounce this wrong, but so the second no-go theorem that you mentioned was the Cauchy-Spekker?
Cauchy-Spekker, yes.
Cauchy-Spekker theorem. So how does that refine Bell's theorem, and what does that tell us?
Good. So the Cauchy-Spekker theorem, so that's from 1967. Actually, so Bell, around the same time that Cauchy and Spekker did their work, had a similar theorem, which established essentially the same result. So it doesn't assume locality. What it does is it says, like, even if I have a single system, so remember the Bell experiment involved this pair of systems where I'm doing measurements on them, but even if I have a single system that I'm sort of preparing in some way, and then I'm doing different possible measurements on it, there's still some interesting structure there. So in quantum mechanics, I can have two different measurements, but say outcome one of the first measurement and outcome one of the second measurement are closely connected in the sense that I see the same probability of getting those outcome no matter how I prepared the system, right? So it feels like they should be measuring the same property, even though the way I carve up the rest of the outcomes are different. That, you know, outcome one of this measurement, outcome one of this measurement seem to be measuring exactly the same thing. So, you know, you can think of it this way: if I coarse grain the outcome of each of these measurements so that it's just outcome one or not, and I put those two measurement devices in a black box, and you get to sort of take those black boxes and put them in front of different preparation procedures and try to tell which box contains which measurement. You can't do it, right? They look exactly the same. So they have this sort of operational equivalence. So the idea of the Cauchy-Spekker no-go theorem is to assume that when you see that sort of phenomena, then assume that they are ultimately, you know, the predictions have a hidden variable model explanation, and the properties that's being measured by these coarse-grained measurements are exactly the same. So that when I can't tell the measurements apart in terms of their statistics, it's because they're measuring the same property. So that's Cauchy-Spekker non-contextuality, that whether outcome one occurs in the context of this measurement or whether it occurs in the context of this other measurement is not relevant to how I model it in this underlying hidden variable model. It should be measuring the same property.
It's context independent.
Context independent, hence non-contextual. Yeah. And so they showed through a very clever argument that even though that sounds very plausible, you can show sets of measurements that have these sort of interesting interconnections between them where it's not possible to have one of these non-contextual ontological models of the quantum statistics. And so, yeah, most people would say it is a less natural assumption than locality. Like, to give up locality is to have this tension with relativity theory, whereas many people would say, well, to give up on this notion that these two outcomes should be represented in the same way, that's, you know, not so bad compared to giving up on relativity theory. But, you know, my impression has always been it is actually a very natural assumption. Why? Because Leibniz's principle says, if in principle there is really no way to see the difference between these two coarse-grained measurements, you know, outcome one versus not for each of these two guys, that no way I prepare the system can ever lead to me being able to distinguish them, not even in principle. And yet my hidden variable model says, but they're measuring very different properties. Well, that's a violation of Leibniz's principle. And the fact that Leibniz's principle was, you know, so successful historically, like in the hands of Einstein, it led to special relativity, general relativity, makes it for me one of the great principles of physics that we should not be challenging. And so for me, the notion of non-contextuality is justified by Leibniz. And I would see Bell's notion of locality as ultimately also being justified by Leibniz. Why should we not assume that there's these causal influences between different regions? The answer is because we can't send signals fast at the speed of light. So in a way, we're imagining that there's something ontological, some influence that's really there, and yet there's no way of sort of turning that into a signal. That's, again, a violation of Leibniz. So for me, it's sort of both of those assumptions, the one in Bell's theorem and the one in the Quotient-Specker theorem, ultimately rest on top of Leibniz's principle. And that's why I see those two theorems as having a very similar status.
Do you have other principles apart from Leibniz that sort of direct you in the decisions you make? So, for example, to maintain locality? Yeah,
I think, certainly like what I said earlier, like a realist explanation for me, if you say, what's the essence of realism? What am I looking for? I would say the model should provide causal explanations of correlations. So, just saying, hey, here's a model and it predicts some correlations, but I'm not going to tell you what the causal explanation of that is. That's a problem. So sort of like the principle that, the underlying model should be a causal model. That's, one of my priorities. I would also say that generally speaking, principles that have been empirically successful in the past should not be jettisoned. I think the history of physics shows that lots of things change under revolutions, but generally what doesn't change are the kinds of principles that get upheld. So like maybe the particular ontology, the particular way you picture what's going on might change, but conservation of energy stays. And the fact that there's action-reaction, that stays. A lot of features like that. So generally, I would say I'm very kind of conservative on the principle side. Like, I hope that we can have an interpretation of quantum theory that puts the sort of strangeness, the weirdness, the innovation in a place that is kind of more nuanced than, let's throw away determinism, let's throw away action-reaction, let's throw away locality. There's like a lot of principles you can jettison. And when I started out my career in quantum foundations, I was sort of working on an interpretation that jettisoned almost everything you can imagine. Reductionism gone, locality gone, so on. And now I look back and I think that there's not much to recommend those sorts of approaches. That the real challenge is to see how much of the sort of pre-existing successful principles can you preserve. And usually there's some sort of interesting way around it, like to evade the no-go theorem. So like when Einstein gave up the notion of absolute simultaneity by giving up on the conventional notion of space and time and preserving the relativity principle and the light postulate. That is, remarkable, because you might have thought, well, relativity principle, light postulate, they're just in contradiction. There's no way to preserve them both. You've got to give up one of them. No, there was another route. There was these assumptions in the background that people hadn't articulated because they didn't see what the alternative was at the time. So why did it take so long to get non-Euclidean geometry? To some extent, nobody saw the alternative, and so there was no room for articulating the assumption, that you would give up. And so to some extent, the problem is you need to find the places where you can modify things that are kind of more subtle. And so now I think it's in the sort of theory of causation and the theory of inference. And by putting the modifications there, while still sort of preserving classical causation and inference in certain limits, we can hope to hold on to things like locality and action-reaction and Leibniz's principle and conservation of energy and a lot of other things like that.
After studying, how many years have you now been spending in this area?
Let's see, I guess probably about 30 years now.
So after 30 years of studying the foundations of quantum mechanics, is there something that still just confuses you? That you like? Is there something there that to you just seems so weird about quantum mechanics that you want to know the answer for, that you just don't even know where to start in some sense?
Let's see. So I would say, for a long time, I've been, looking at certain aspects of the phenomenology of quantum theory and trying to come up with classical Leibnizian models of them. And, generally I can sort of see how that works. But one area that kind of has eluded me is particle statistics. So, the fact that there's these two types of particles, bosons and fermions, and bosons exhibit bunching behavior in these Mach-Zehnder type interferometers, and fermions exhibit anti-bunching behavior, and there's the Pauli exclusion principle. And I think that a lot of that phenomenology, I should be able to find a classical model to reproduce it. But it's the fermions have caused problems that so we're still working on that. It still kind of bugs me, and I haven't quite seen my way through to that.
Can you flesh that out a bit more? So in what way do they cause problems?
Well, okay, so I guess these days, like we discussed earlier about interference, my impression of how do you have a classical Leibnizian model of standard interference phenomenology? You give up the particle ontology and you embrace a field ontology, right? And you can kind of understand the particle ontology as a kind of coarse graining of the field ontology. So if I say, okay, look, there are fields and they have these excitational degrees of freedom. So the left mode and the right mode, left mode's occupied, right mode's unoccupied. Well, that's a bit like a particle that's going left rather than right. So I can kind of reproduce the particle language using my mode ontology. And I suspect I can do the same thing for bosons and fermions, that ultimately they are fields, and a lot of their phenomenology could be explained by sort of a classical field theory, where now I have probability distributions over those classical fields, which are going to mimic the wave function. And I should be able to reproduce the kind of particle picture, which for bosons says if I exchange two particles, nothing changes, and which for fermions, if I exchange two particles, then the phase of the wave function changes. It picks up a negative sign. And so that's the challenge that I haven't been able to meet at this point. But it's on my mind because we're thinking about this now. So it's just been on the list of things to do for many, many years, and still haven't got there. So it's one of those things. And one of the places I'd like to go, I do feel that, it's connected, quantum electrodynamics, which is the theory that, not just of the electromagnetic field, but of how those interact with charges. Elsewhere in my research, I've been able to show that there's these parts of quantum theory that can be explained with these classical Leibnizian models. The Clifford subtheories, right. So in quantum computation, if I have a quantum circuit and I restrict the kinds of transformations I'm allowed to apply. So I have only certain kinds of gates, and I restrict the kinds of preparations, and I restrict the kinds of measurements. I can still have a really rich theory that involves entanglement and interference and no cloning and teleportation and whatever you like, most of the stuff that's on the list of things that we think of as surprisingly quantum. And yet the whole theory admits of one of these classical Leibnizian models. And so anything I can get in any circuit that I build out of that can have such an explanation. So it's not just sort of like one little circuit, but anything you build. So that's quite powerful. If you can prove that, it sort of says, hey, there's a whole bunch of big part of quantum theory here that you can explain classically. And it's the same if you talk about particle mechanics. If I have a collection of particles, there's a restriction on the preparations of those particles and the dynamics and the measurements on those particles that goes under the name of Gaussian quantum mechanics. And you can show that all of that also has one of these classical Leibnizian models. And so anyways, that's sort of the pattern, that you can sort of go to these different parts of quantum theory where you're looking at different collections of systems and ask, is there some sub-theory that can be modeled classically? And so it's always struck me that quantum electrodynamics should admit of some sub-theory that maybe I can have a classical model of. But it's tricky for the same reasons that it was tricky to ultimately get to quantum electrodynamics, that it doesn't have a natural Hamiltonian formulation. To me, you really need to treat the charges and the particles as fields rather than particles. But now they're fermionic fields, and so you kind of need to solve that problem of how to model fermionic fields in a classical, one of these classical models. So that's another problem that's kind of just bugged me for a long time, that I haven't been able to get through that. Hopefully, we'll see progress. And then maybe the other example I would give is that there's a recent set of results that go by the name of Wigner-Friend type arguments. So there's been a kind of resurgence of these in recent years where people have no-go theorems. And I can't reliably say which of the assumptions of those no-go theorems I have a feeling of which one I should give up, and how this research program I described to you, manages to evade the contradictions. But I'm not confident about that. So it's sort of, something that's sort of on the list of like, oh, maybe when the research program's further along, I can go back and see how do I respond to that no-go theorem.
Do you think, so is there a good chance that someone will bring out a no-go theorem that crushes the program in some sense, that says that, you know, the wave function really is
Right.
a state of reality, and you
Yeah.
really can't fit it as a set of knowledge?
Well, okay, I'll answer yes and no in a way. So the no is kind of like, you know, generally no-go theorems come with a list of assumptions, and typically, if you really want to evade the contradiction, you'll be able to find some way out besides the thing that you want to hold on to, right? Like there's always, in philosophy of science, people talk about auxiliary hypotheses. So if I see some anomaly in the solar system, I can say, oh, it's because there's some planet I haven't observed, not because the laws of gravity are different. And so generally, it's rare to say, oh, here's a theorem, and now I abandon the sort of main heuristic of my whole research program just because of that. Usually, there's a way out. But what I would say is that, I mean, how would it happen that I get persuaded that I've been on the completely wrong track, and you know, this idea of the wave function as being epistemic is somehow misguided? That could happen, and you know, so let me try to explain what I think would have to go down. So this is where I'll wheel in this analogy with the decipherment of Egyptian hieroglyphs. So bear with me. I use this analogy mostly to talk about category mistakes. So what I like to say about quantum theory is that, you know, the reason that we haven't got a good interpretation is that, you know, for most of the history of quantum theory, our interpretation of the wave function has involved a category mistake, that we've assumed it describes, you know, reality when in fact it describes knowledge of reality, and that has kind of impeded progress. And so the historical comparison I like to make is when people were trying to decipher Egyptian hieroglyphs. So this is like at the end of the 1700s, and you know, nobody knew, like back in, you know, 500 AD. That's probably when the last scribes who were writing hieroglyphs died. You know, so you know, a long time had passed, and so it really was unclear what this was. And the main idea then was that the individual glyphs were ideograms, so they represented concepts. So kind of like airport signs, you know, it's not representing a word per se, it's representing a concept. And so people had these elaborate interpretations of hieroglyphics by sort of mapping up signs to concepts. And then it was discovered by Thomas Young, the same guy who did the double slit experiment, which we've been talking about. He also had an interest in the decipherment of hieroglyphs. He, you know, building on the work of others, realized that certain special sets of signs, which were in these little loops, which the French soldiers who brought back some of these things called cartouches, because it looked like the shape of their bullet casings. So inside the cartouches were sets of signs which he realized could be interpreted phonetically to spell out the names of pharaohs. So he had some evidence that, like, he could say, okay, well, this sign has this phonetic reading, and so that this one spells out Ramses, and this spells out Cleopatra, and so forth. And so suddenly they had this completely different type of interpretation of the glyphs, is that they're phonemes. They're representing sounds of some spoken language. And the surprising thing is that you imagine then the next thing to do is just, okay, well, let's interpret it all phonetically and see what comes out. But they resisted, and they said, well, maybe it's you know, proper names of people are things that you couldn't easily represent with concepts, and so there you'd have to resort to a phonetic, but for the rest of it, you would not. And so for a long time, they still struggled and assumed that everything was ideograms rather than phonetic, and finally, a Frenchman by the name of Champollion decided to interpret it all phonetically and figured it out. And you know, nobody knew what language was spoken by the ancient Egyptians, right? And it wasn't even clear whether that language had survived to that day. So if it hadn't, there would be no way to do a phonetic decipherment. But it turned out it had survived in this, the Coptic Christian church, like the liturgy. And so the word Coptic actually comes from the same root as Egypt. And it all made sense that, like, Champollion knew Coptic. And so he started seeing the grammatical patterns of Coptic and realized this is all Coptic. And he could, on the Rosetta Stone, you had it in Greek and in hieroglyphs. So then when he could, read the hieroglyphs, he could compare it to the Greek and see that, oh yeah, this is really the right way to do it. So there, the category mistake was thinking that the glyphs were ideograms rather than phonemes. Mm-hmm. And once you correct that, you suddenly things make sense. Okay, so I believe that, Clifford subtheories, and what we were talking about a moment ago, are kind of like the cartouches. There it makes sense to interpret quantum states as states of knowledge, and everything works out very nicely. And it fits very coherently. We have a good notion of causation and inference. But to sort of get everything interpreted in that way, where quantum states are states of knowledge, that's where I kind of need the innovation of this exotic type of causation and inference. I need to go beyond sets and functions. That's like having the Coptic language, right? Like these proper names of pharaohs, I didn't need to know what language that was in. They would just sound the same in all languages. But to do the rest, I need to know what language is spoken. So that's kind of like where we are. But it could have happened in the case of hieroglyphs that the people who said, look, the cartouches, by virtue of being proper names, that's the exception. That's the only case where it's phonetic. They could have been right. And then, maybe...
Which would be very weird.
It would be strange, but to some extent I could imagine maybe the ways in which all the rest of it really were ideograms and not phonetic, and they were right. And the explanation of like in this alternative history, somebody would try to interpret it all in terms of phonemes and somehow fail. And then, they would say, but why? How could it be that these cartouches are phonetic and the rest is not? And the answer would be, well, proper names are, not easily expressed in terms of concepts. And so if I'm wrong about the quantum state, then there would have to be an explanation like that. Like, look, you were deceived. Like all these strong, powerful analogies between how quantum states can be teleported but not cloned and not distinguished and so on, it makes them all look like probability distributions over some underlying space. And we didn't talk that much about all the evidence, but I would say there's a very large body of evidence that you should think of quantum states as being like probability distributions, and hence in the category of things that are epistemic. Somebody would have to come to me and say, here's why that was all misleading. It's not like that. But here's how you got stuck in that trap. It's this other thing that you didn't anticipate, kind of like the proper name thing. So if that happened, and so like somebody explained to me why it was that there was all these powerful analogies, but it was all a red herring, then maybe I would change my mind. But for the time being, there isn't a no-go theorem against this research program, and so I continue.
So let's say that your research program is completely successful, and in the next 30 years we develop a complete description of quantum mechanics, and when we understand the theorem.
Yeah.
What is that theorem going to look like? What's your guess for the way that...
What will quantum mechanics look like, under the correct interpretation?
Yeah.
I guess it will be a bit like... okay, so a few things that, one of the things we didn't talk too much about was like that third branch of stuff we do in quantum foundations, which is try to understand and locate the theory within a landscape of possible ways the world could have been, and sort of find principles that pinpoint quantum theory. So I think one of the nice things about, getting the right interpretation is that we can be much clearer on sort of what principles pick out quantum theory. What are the principles that sort of make the world have to be quantum rather than classical, for instance, right? So we'll have a much better understanding of those principles. And I think, history has shown that like having a principled understanding of the essence of a theory is really key for moving forward. So like if you look at Einstein's discovery of special relativity, he was not the first person to write down the Lorentz transformations. That's why they're called Lorentz transformations. He already had those. His contribution was saying, I can derive those transformation equations for space and time from these postulates, the relativity principle and the light postulate. And that gives you a much deeper understanding of what they embody, those equations embody. And I think without that understanding, he would not have been able to build general relativity, right? So the whole idea of trying to extend this relativity notion to accelerated observers and observers at rest in gravitational fields, that was really built on the success of the special theory of relativity. And so I feel like those principled understandings of theories are really important as stepping stone towards the next thing. So if the research program works out, and in the end, there's a modified theory of causation, a modified theory of inference, and furthermore, that new formalism that describes causation and inference maybe can be boiled down to some principles. Like, oh, we thought that causation was like this and inference was like this, but actually there's this small change, kind of like the way that time doesn't have absolute simultaneity. It's a nuanced kind of change in how we have to think about this. I think that new kind of conceptual understanding will be key to sort of moving forward and progressing physics. Maybe, for instance, it might make it clear how you might want to unify quantum theory with general relativity. but also, how you should think about quantum computation and quantum machine learning and causal inference and all those other things.
Well, Rob, thanks for coming on the podcast.
Oh, thanks for having me.